It's a great pleasure for me this afternoon to introduce Dr. Martin Hoffert. Dr. Hoffert has really written the most pivotal works in the last few years on the subject of fuel choices and global warming. He's really made a tremendous contribution to the debate, and if you go to your programs, you'll see the reference to the two titles and reference to the two articles. Everybody here, your assignment for the conference is to go home, download those articles, and read them. He is at New York University, and his research interests include energy science and technologies, global climate change, oceanography, biogeochemical cycles, fluids plasma, and wireless power transmission. Thank you very much, Dr. Hoffert.
Well, first let me say what an honor it is to have been invited to this august gathering, one that I have an enormous amount of personal sympathy with as far as the goals are concerned. Let me also just quickly as I can be quick, say what was the sort of genesis motivating the papers that were referred to and the talk I'm going to be giving today. My own career actually starting about 25 years ago when I worked for the Goddard Institute for Space Studies in New York City. I actually had changed my field. I had been working for the defense establishment, which is another story. And I sort of was interested in doing something that might be more, let's say, socially benign. It was the 1960s, late 1960s. And I went to work, I started working for this Goddard Institute for Space Studies, which is in New York City. It's affiliated with Goddard Space Flight Center in Greenbelt, Maryland. And myself and several others who also became notorious in the climate change field, we began to look at this problem that's now called global warming, or climate change that's induced by human beings, by the insertion into the atmosphere of so-called greenhouse gases, primarily carbon dioxide produced by fossil fuel burning, but there are also other greenhouse gases. And I thought this might be a good field to get into. This was in the early 1970s. I had looked at a few graphs which showed that the concentration of CO2 was rising in the atmosphere. And the theory of global warming is actually 100 years old, over 100 years old. It was originally proposed by the Swedish chemist savant Arrhenius. But by the early 70s, there were some pretty good studies on how the atmosphere worked and why greenhouse gases were absolutely critical to understand the structure of our own atmosphere, not only the atmosphere of Earth, but also other planetary atmospheres, the atmosphere of Mars, for example, which is warm enough at the surface to melt lead, and that's entirely due to the greenhouse effect of a very thick carbon dioxide atmosphere. Some of the discoveries that had been made in NASA's space program, particularly the discovery by the Viking spacecraft, that there were what seemed to be channels or riverbeds on the planet Mars when we started mapping it in great detail. I mean, they weren't the canals that Schiaparelli had predicted years before with living Martians in a civilization, but in some ways as interesting because Mars is 55 degrees Celsius below zero and there should be no liquid water. However, a theory of planetary evolution that had Mars had an early atmosphere of carbon dioxide would have explained that earlier epoch when there was liquid water on Mars. Not to mention our own planet Earth. Most astrophysicists know that stars like our sun, as they burn along the main sequence, they increase their brightness so that when the Earth first formed and life began to exist, it was 30% dimmer, the so-called dim sum problem, not a Chinese restaurant, an actual kind of paradox in atmospheric science is explained by the presence of an early dense carbon dioxide atmosphere. And we've since learned that even satellites like Saturn satellite Titan it has greenhouse gases in them, and they all basically are explained by this theory. Not only that, but geologists have discovered all sorts of paleoclimatic evidence. Ice cores in Antarctica drilled down to the floor can reveal a history going back 420,000 years in which you can actually see several ice age, inter-ice age cycles, and those cycles actually one can determine the temperature variation of the Earth and also the carbon dioxide variation content of the atmosphere, and you can actually see how changes in the CO2 concentration of the atmosphere were positive feedback, produced the positive feedback that caused a certain amount of global cooling during ice ages and warming during inter-ice ages. For the last 1,000 years, roughly, paleoclimatologists have reconstructed records of the Earth's surface temperature and overlap them with the instrumental history so they both match during the period when you're looking at them at the same time, roughly for the last 100 years. And these clearly show that there's been a spike in global temperature associated with the increase of carbon dioxide. Now, there's enough fossil fuel in the fossil fuel reserve. There's at least 5,000 gigatons being billion tons of carbon in the fossil fuel reserve, and there's about 700 gigatons in the atmosphere. So if we were to burn all of this fossil fuel, we could raise the CO2 concentration, which has already increased from about 270 parts per million to 360 parts per million, but there's enough to make it go up to 1,200 parts per million. That is if we burn all the coal and we burn all the oil. And we do think that the Earth at one time did have such high concentrations of CO2, and that was during the Middle Cretaceous, roughly 100 million years ago, when the average temperature of the Earth was, in Celsius, 10 degrees warmer than it is today. That's 18 Fahrenheit. And the Earth was completely deglaciated, and there were dinosaurs in Antarctica and reptiles at the pole. It was a tremendously different planet at that point. And it became clear to me, although this happened gradually over this 20 years when I got myself into this field, that humankind has this ability to dramatically transform the planet. Not only that, it's not just that the CO2 is increasing in the atmosphere, but CO2 is very long-lived in the atmosphere, at least a fraction of it. And we also have the ability to shift the carbon dioxide carbonate equilibrium of the air-sea system so that we don't get back to the pre-industrial values. In other words, you don't sort of regain your virginity if you burn enough CO2, but it's a long-term change. Whether this is good or bad, I mean, the three separate questions in global warming. The first is it real? Is it scientifically justified that human beings have altered the average temperature of the Earth and will continue to alter it in the future by continuing to burn fossil fuel, is one question. The second question is, if that is true, what is the impact of that? Is that going to be beneficial, as some people, a minority, think it will, or will it be basically deleterious? Will it happen so rapidly that ecosystems are going to become extinct, that rainfall patterns are going to dramatically shift, affecting agriculture, that tropical disease vectors are going to move into places where they've never been before, and that finally ice caps like the West Antarctic ice sheet are going to become vulnerable and sea level will rise, inundating the coastlines not only of Pacific nations but of our own country. And the third question is, if global warming is real, if the impacts are bad, is there anything we can do about it without destroying the world economic system? Now, we've heard a lot of really fascinating, I was going to say tales, but I'll say talks about, you know, the liquid hydrocarbons, their abundance and how long they're going to be around at current rates of consumption. But the fact is, if we talk about fossil fuels generically, which includes coal, we don't really have to worry for this century. I mean, there's enough coal, and we can make synthetic gas and synthetic gasoline out of coal if we're willing to tolerate the downsides of it. And so that was sort of the conventional wisdom back in the 70s. Some of you may be almost as old as I am and remember the gas lines of the 70s and the Carter energy plan when people actually were spending some money on alternate energy. Anyway, we built coal gasification plants then, and it had been done earlier in South Africa, and the Germans did it. And so we could make do for this century without a dramatic and fundamental change away from fossil fuels. It would still be an energy revolution, but it wouldn't be a fossil fuel revolution. But what global warming has done is it has caused an acceleration in this agenda. And we may have to go through a radical transformation of the energy system before then. And that has enormous implications. And so about 5 years ago, we started to study some of these problems. And along the way, I managed to collect a group of collaborators. And mostly these are engineers and physicists, but also some reformed economists as well. I mean, there are different ways of looking at this problem that economists have and that engineers and physicists have, which is something that I learned. And so the talk that I'm going to be giving is what we learned treating the problem of mitigating global climate change as a problem in science and engineering rather than as a problem in economics. Not that there are important economic components to it. What are the physical limitations? What are the physical constraints? What are the specific technologies? And the idea here would be to try to identify strategic technologies and strategic areas that we might want to emphasize in a research program. If we ever became, in my view, rational enough to realize this root problem of developing a new energy system that might be more sustainable than the one that we have, and we became serious about it, what are the kinds of things we have to study? What are the technical hurdles that we have to overcome? And there were some papers that came out of this, including a paper in Science in November, and if I have time, I'll talk about those. So let me get started and with understanding that as the genesis of this work. Some of the material is a little technical, and I won't belabor it, but it is important to get some of the main numbers out. So let's see. Okay, this is the paper that I mentioned. You might want to look at this. It was published in Science on November 1st, 2002. A very recent issue of Science, April 25th, you can read 3 very angry letters by people who read this article, and also our response. I mean, the anger is kind of masked by this sort of phony politeness that you have to use in writing these things. But really, maybe the issues, see, from our point of view, if we felt all along that this issue, the alternate energy issue, it was kind of like our experience, and there were 17 people, including myself, who worked on this, and more had been on it. Some people resigned in protest. One of our co-authors resigned to write a book to refute the paper. It almost functioned like a psychological projective test, a Rorschach test, where people's own views about sustainability and about ultimately things like politics were reflected in their response to these particular issues, because these are very, very highly politicized issues, in addition to being very fascinating engineering and science issues. So you can read this paper. Okay, one of the things that we did was to try to look at the factors that influence the emissions of CO2. We're emitting right now about 6 gigatons of carbon, or gigatons, however you pronounce it, 6 billion tons of carbon into the atmosphere from our human activities. And since there are about 6 billion people, that means every person puts about 1 metric ton of carbon into the atmosphere in the form of CO2. That's a lot of carbon, and that's really the reason why carbon dioxide levels have gone up and why we think the Earth is beginning to warm. But you can deconstruct those emissions in in terms of this kind of equation that's an identity at the top. The CO2 emissions, I don't have to stand there. CO2 emissions are the product of 4 factors. The first is population, and that's shown, let me just say that the scale, which has been cut off, no it hasn't, the scale on the horizontal axis is years. The scale runs from 1900 to 2100. The year 2000 is in the middle. So everything from 1900 to 2100 to 2000 is historical data, and everything from 2000 to 2100 is a projection according to a scenario into the future. Okay, the first graph shows human population growth and shows, as you know, human population crossing about 6 billion around the year 2000. The second is per capita gross domestic product. You just take the gross domestic product of the world at any particular time, and how many and what that is divided by the number of people, and that's been increasing. That's been increasing at a rate of about 1.6% per year, and the projection is it will continue to increase. Now this is for the mean of the world. It's not the median. Energy is very wealth and energy are both very inequitably distributed, as many speakers have already pointed out. The third quantity is the energy intensity, and that's the energy per unit GDP. And you can see in the last century, it first began to increase and then to decrease. And the projections of most of these models is that it will decrease about 1% a year. Now, this is where efficiency comes in. This is actually the efficiency of making money out of energy. If you take the gross world product and divide it by the energy use, it's about 23 cents, per kilowatt hour. Every kilowatt hour of raw energy, you can think of it that way, generates 23 cents of GDP. Different countries are more efficient than others. The Japanese may be able to do 46 cents of GDP per kilowatt hour, and some of the former Soviet Union nations did worse, like 12 or 13 cents. So there's some variation, but that variation is very small compared to the absolute difference in energy per capita or GDP per capita between a rich country like the U.S., where you're talking about maybe $20,000 or $30,000 per capita, and a country like Bangladesh, where you may be talking about $200 per capita. In fact, you need 3 or 4 logarithmic cycles to plot the energy versus GDP data, and I won't go into this anymore now. The final quantity that goes into this equation, it's called the Kaya equation, is the carbon intensity. It's the amount of carbon per unit energy that's emitted, and that is different for different fossil fuels. Coal produces the most, and then oil, and then gas, which is a lower carbon fuel. And in the business as usual scenario, we were surprised to find that by the 21st century, by the year 2035, they were already assuming, the people who made this scenario up, that the average carbon intensity would be less than the carbon intensity of gas. Now, the only way that can happen is if there's a humongous amount of CO2 emission-free energy, that is, energy that doesn't emit any CO2 to the atmosphere, and that had been built into the assumptions. If you multiply all these numbers together, it gives you the CO2 going into the atmosphere as a function of time in the 21st century. And if you know the emission factors of the various fuels, you can actually work out how much energy, how much CO2, what the CO2 concentration would be of these emissions. The concentration and the emissions are not really the same thing. You can also do another problem where you can say, suppose I wanted to stabilize CO2 in the atmosphere at some level, be it 350 ppm, 450 ppm, whatever. I can also do a calculation that says if I'm going to grow the gross domestic product at a certain rate, which we use the business as usual rate, and I'm going to improve energy efficiency at this 1% a year rate, then the total energy demand is constrained, and the allowable amount of energy is constrained by the allowable CO2 you can put into the atmosphere as a function of time in order to stabilize at some level. So what you get out of that is how much emission-free power you need to have from some energy source X. And that's what this curve shows. These two curves. The curve on the top, let me see if I can do this without, yeah. Forget about this inset. It is very insightful, but forget it. This is historical CO2, and you can see it going up from 300 parts per million to 360, and then by the end of the century, reaching about 700 parts per million for the business as usual scenario. That's with emissions computed as I showed before. Now, the stabilization scenarios say, suppose eventually I wanted to get to 350. Now, you see, you have to go up and down. You're going to have to suck CO2 out of the atmosphere because it's already 370, so you're not going to be able to just asymptotically increase to that. I knew this was going to cause a problem, but maybe it's not irreparable. So that's what the top curve shows. Shows the amount of CO2 according to business as usual and according to these stabilization scenarios. And we don't pick one, but actually people who look at impact say that, for example, if even 450 parts per million would be sufficient to cause irreparable damage to the world's coral reef system. And 550 ppm, which is a doubling of the pre-industrial level of CO2, will eventually melt the West Antarctic ice sheets. Definitely, I would sell your waterfront property. I had actually some of that in Boca Raton, Florida, and my wife and I decided after we did this analysis that we should definitely sell. And we did. Now, I have to be fair. This is probably going to take a few hundred years to work itself out, but these are just some of the kinds of the impacts. Now, the lower curve is actually in some ways more interesting because this shows, I can't really use this pointer without taking a chance on the whole thing collapsing, but this curve, the upper boundary of this curve, is the total energy. You have a laser pointer. That's wonderful. Except I'm on the wrong. Just bear with me, folks. Here we go. Okay, this curve is total power consumption. And you see by mid-century, we're talking about something like 12 terawatts, of which 10 terawatts, the units are terawatts here, of which 10 terawatts is from fossil fuel consumption. And this is the value of the total energy consumption, which is calculated, as I showed in the previous graph, by multiplying out the GDP over N and the E over GDP numbers. Now, this graph shows the amount of non-CO2 emitting power that we would need for various scenarios. For business as usual, and we didn't realize this until we had done this analysis, by the year 2050, for business as usual, which means just the normal economics, of normal working out of the economic system, the authors of this scenario had built in 10 terawatts by 2050. That means that by the year 2050, less than 50 years from now, we would be producing roughly the same amount of power that our entire global energy system produces from fossil fuel, from some non-fossil source. Let's call it energy source X. To give you an idea of how incredible that is, or I shouldn't say incredible, I should say challenging, because I don't think it's incredible. I think we can do it. And no matter what I say, I have a basically positive message. The first reactor, Fermi's first nuclear reactor in 1943, was farther in time than 2050 is. And nuclear power today, this is primary power, thermal power, not electrical power, is 5%, less than 5% of our total energy. So we have to have some energy source that will scale up by a factor of 20 relative to what nuclear power has done just to be business as usual. So we think that's a pretty optimistic assumption for business as usual, but it's still not any of the stabilization scenarios. If we wanted to stabilize at 550 parts per million by 2050, we would need 15 terawatts. If we wanted to go back to 350, and there are environmentalists who say that we should do that, we would need something like 30 terawatts. At least we probably need more than that, because we'd have to devote some energy to removing the CO2 that would already be in the Earth's atmosphere. Now, I do want to say there are differences of opinion. That scenario was developed by the IPCC, that's the Intergovernmental Panel on Climate Change, this United Nations sponsored organization of thousands of scientists. And not every energy company agrees. We heard about BP, for example. But ExxonMobil, and I should, in truth in advertising, admit that I actually used to consult for them, has a different view. This is from one of their op-ed editorials they publish in the New York Times op-ed page. They actually pay for this, for their point of view to come through. And actually, I don't think this is such a bad analysis, but it's making slightly different assumptions. They say, well, this is the total energy, and this is from 1980 to 2020. It doesn't go from 1900 to 2100. So this is sort of today, and of course they're using millions of barrels a day equivalent rather than terawatts, but because they're an oil company, but this is about 10 terawatts here. And so this black area is how they foresee total energy demand going up, and the upper part being developing nations. Now, the interesting thing is that this gray area here is the non-fossil component. And of the non-fossil component, this big, now we're spreading this out, expanding the scale, this piece is nuclear, hydro, and biomass. And this little tiny sliver here is wind and solar. I mean, an incredibly small fraction of 1%. Even though, if you expand this scale, the solar and the wind are growing exponentially. They're starting from such a small base that even by the year 2020, they represent an extremely small component of the total energy picture. And so part of what we started to look into, how can I erase this? Maybe I'll go to the next. Oh. That's all right. It's okay. Yeah. I'm a Mac person, but if I have to, I'll use a Wintel machine. It's really painful psychologically. This is now, we get most of our energy. Well, I mean, we're talking about the market. There's difference of opinion between how technologies get developed, whether sort of classical Adam Smith economics, the best technology is always going to win. In which case, why doesn't everybody have Macintoshes? Why are there so many of those Windows machines? Okay. Now we actually get most of our primary power that in the form of electricity comes from hot water. Today, we basically make steam by burning fossil fuels. You guys all know this. You're in the energy business. And right now what happens is that the CO2 goes up the stack. So one of the technologies that's getting a lot of interest in the Department of Energy now has to do with the sequestration of carbon from fossil fuel power plants. And this is basically from centralized power plants. Now, we wanted to ask the question, and we keep asking this question about terawatts, which is also an important question for this meeting. If you wanted to do 10 terawatts with this technology, what burial rate, how fast would you have to bury the carbon? And the idea, let me just tell you what the basic technology is that you have fossil fuel coming into to a centralized power plant. You make electricity and or hydrogen. You separate the CO2, and you put the CO2 either into deep underground aquifers or coal beds, or somehow you put it into the ocean, but you get it out of contact with the atmosphere. And that has problems too, because if you put all the fossil fuel reserve, 5,000 gigatons, and you put it underground, then if you have a leakage rate of only 0.1% per year, that becomes 5 or 10 gigatons a year going into the atmosphere. So you have to make sure it's very secure. But forget all of that. Just think about the materials handling issue. Anywhere from 5 to 10 gigatons a year have to be stuck back into the Earth somehow or other. That's a huge, think of it as a huge inverse coal mine that you're putting stuff, except it could be gas. It depends on whether you're putting it back as solid or as gaseous carbon dioxide. We have the technology. We're doing stuff like this now in secondary oil recovery, but it has to be scaled up by a factor of 1,000 to get close to this 10 terawatt level. So that's a major technological issue, and that is something that needs to be studied. Now, it's even more radical than that is an idea that advanced by my colleague Klaus Lackner, who said, well, yeah, but that's only for centralized sources. What about decentralized sources? What if this hydrogen stuff doesn't work and we're still running cars with gasoline? Or what if we do use fuel cells, but the cars have reformers, which are little onboard chemical factories that make the hydrogen out of gasoline or methanol? They're going to vent their CO2 into the atmosphere. So you're still going to have CO2 going into the atmosphere. You may want to take that out. In fact, maybe that would be a good thing to do. Then we wouldn't need hydrogen, which is going to be so complicated, and we don't know what the infrastructure is going to be yet. So there is research going on now in chemically extracting so-called air capture of carbon dioxide from the atmosphere. I mean, any one of these things I could really go on and discuss at length, but at this point I think it's more important to give, this is again I did this stupid thing, to give the synoptic view. Now, the Jeremy Rifkin talk, which I actually found quite fascinating for reasons I won't go into, but I did find it fascinating. The issue came up about infrastructure, okay? Infrastructure of hydrogen. There are actually different ways to go. I mean, we are talking, first of all, let's, again, put the facts on the table. Photovoltaic cells certainly work, and the cost per unit photovoltaic cell is going down. However, even if they were as cheap as toilet paper, there would be a serious problem of distribution and storage. But the scale problem is important to emphasize. 10 terawatts. Let's not even talk about running the world with 10 terawatts, because 10 terawatts thermal is only 3.3 terawatts electrical if you use standard conversions. If you wanted to just provide all the electricity in the U.S. with PV panels and put them in a Nevada desert, as someone had suggested in an earlier paper in Science, it would take something like 220,000 square kilometers. Keep that number in mind in your short-term memory just for a while. All the PV cells that have been manufactured since we started making them cover how much area? Anyone have a clue? Take guesses. How many square kilometers of PV cells have we made so far? Well, you're 2 and 10 are the right order of magnitude. The number is 3. Okay? So we're talking about here a scale up in simply the physical area of a factor of 10,000? 100,000. Yeah, it's easy to lose an order of magnitude when you're doing these problems. Now you will see that in later things that I'll touch on briefly if I have time, and that my colleagues, John Mankins and Dave Criswell, will expand upon tomorrow. There are a number of advantages of putting these solar collectors in orbit around the Earth or on the Moon. But let's say we're talking about putting them on the Earth. We've got this enormous scale-up factor. Apart from the scale-up factor, we need a way of integrating them. And I do agree with Jeremy Rifkin that we do need some kind of smart grids that will accept this power, because the basic problem with both wind and PV is that they are very low power density. I mean, compared to a central power plant, they're about 15 watts per square meter, and that's several orders of magnitude down from power plants. They're episodic, they're not always there, and they're not available Where you need them, they may be in remote locations. So you have to have a distribution and storage system, and the problems of a global energy supply by renewables are very different than the problems of getting renewables into some niche market. If I just want to make a company that will make money on renewables, I'm asking different questions than I am if I want to run the world on renewables, particularly as regard to transmission and storage. And here you have, for example, one path which would involve electrolysis of water driven by renewables, and then that hydrogen could go into a pipeline. It's also possible to make reversible electrolyzers that run as both fuel cells and electrolyzers, and that's one of the issues that we have to solve with regard to what the infrastructure is going to be. Is it going to be decentralized or is it going to be centralized? But there's another path which I like perhaps even better, or at least in parallel. Oh, I do want to say that we don't pick winners and losers. It's very hard to do that, and that's a whole other subject of the notorious difficulty of predicting the technological readiness of technology. Eminent scientists are almost always wrong about this. We should let the markets do it. But what we do need to do is we do need to have an aggressive Apollo-style, except maybe much bigger than Apollo, research program to create the options that markets can select from. And what I'm doing now is discussing some of the options that we looked at. So these mass-produced and widely distributed PV arrays and wind turbines might eventually generate these 10 to 30 terawatts. But here's an idea of Bucky Fuller, apart from, he didn't only talk, we don't only have C60, we have this other thing, which is an icosahedron, which has 20 sides. It's also got these equilateral triangles. And Fuller liked to use that map projection based on icosahedron. He called it the Earth-Ocean projection, to show that if you looked at the continents, the distribution in the right way, there were certain places where the distances between continents weren't that great. And he said, well, why don't we have a global electrical grid? If we could have a global electrical grid, right now electrical grids will, practically speaking, go over hundreds to perhaps thousands of kilometers. But if you could really reduce the conductivity of the transmission enough, then you could collect solar energy on the daytime part of the Earth, and you could sell it to the nighttime part of the Earth where people want to put on the lights. You could do a lot of other good things energy-wise. For example, you could generate nuclear power here in Houston and sell it to North Korea. And because, right, you would sell the electricity to North Korea, or even a renascent Iraq. And so it just shows that, that technologies, that enabling technologies can allow you to do certain things. And I can't wait for Rick Smalley to explain to me how we might actually be able to do something like this with nanotechnology. Moving right along. There are other places that might make sense to put solar collectors. And one of the reasons for putting solar collectors in space is that when you're outside of the Earth's shadow cone, the flux, the watts per square meter, is between 8 or even 10 times higher than it is on the surface of the Earth, for one thing, because it's the difference between the disk area and the Earth's surface area is a factor of 4, and then there's another factor of 2 from the clouds, and then there's some more losses from absorption. So if you could collect that energy and beam it to the Earth by microwave, there might be an advantage, particularly if you could put these collectors where the sun is always shining, and you could target particular locations. I happen to like solar power satellites conceptually as a technology for developing countries, a potential leapfrog technology. And I know there are many, many technical issues, and I don't have the time to go into all of them, and they have to do with things like access to space costs, and John Mankins will maybe be talking about it. But the main advantage, just think about it, there are countries in this world that are never going to have telephone landlines. They're just never going to have those poles with the wires on them. They're going to go straight to wireless telephones. we have the technology to wirelessly beam power directly to the surface of the Earth at relatively high efficiencies. Most radar and microwave engineers believe that it's possible to do this, and we understand the physics reasonably well. And so imagine one future, energy future, where tropical developing countries actually bypass the fossil fuel stage of their development and go directly to wireless power, which is beamed to them from space. Now, such a system would, of course, have to be developed by the developed countries, capital-intensive countries. And we could talk about how this could happen, and we could talk about the economics. But I'm just saying, from the point of view of engineering and physics, there are a number of advantages to this, as there are to lunar power systems. And I won't say any more about this because Dave Criswell, I'm sure, can do a much better job. And you'll be hearing him tomorrow. A solar power satellite is basically composed of a few elements. It's got a solar power collector. It's got a transmitter, which is probably a phased array that creates a microwave beam. It transmits to the surface to something called a rectenna, a rectifying antenna, and that goes into some power conditioning, and that goes to some consumers. So I've been talking a little bit about some of the applications of space technology to alternate energy, and I've been hoping to convince NASA, although we have a small component of NASA who's already convinced, but some people in management, that they have a role to play not only in detecting climate change, which they have a big program in already, it's called Mission to Planet Earth, but in the possible mitigation of climate change. Now as we're moving a little bit out into the more science fictional areas, some people have proposed, and this is a project that's being worked on at Livermore. Edward Teller, who's still alive, likes this idea a lot. As you look at the Earth's orbit around the sun, there are certain points called Lagrangian points that rotate at the same angular velocity as the Earth around the sun. And one of these points, the L1 point, if you were to put either something to block the sun, or in this case, a lens that would just deflect the sun's rays by enough to reduce the solar flux hitting the Earth by a few percent, you might be able to compensate for the global warming from CO2 in the atmosphere. Unfortunately, this guy has to be pretty big. We're talking about a few thousand kilometers in diameter, although it might only be 10 microns thick. This would probably be made on the moon and assembled in space, and there are people who are thinking about this. Now, that sounds like a totally insane idea. Consider the fact that, more seriously, people are thinking of putting aerosols into the upper atmosphere, the stratosphere, much as a volcano does when it erupts and changes the climate that way, to scatter the radiation from the Earth to compensate for global warming. This is a class of approaches called geoengineering, where you try to compensate for the changes in the Earth's radiation balance by blocking it or alternately changing it, but it lets you keep burning fossil fuel without sequestering or any of those other expensive things. Now, whenever you get into a discussion, in my experience, about global warming, there's a community, very active, and in my experience, quite resentful community of nuclear physicists and engineers. And I understand this. I mean, these guys spent a long time going to school and nuclear power has been around for a long time. There even used to be departments of nuclear engineering. Does Rice still have one? Does anyone know? No. And people, would actually study to be nuclear engineers, and they would learn all these hard things about neutron diffusion and everything. And as we all know, since 3 Mile Island, and particularly since Chernobyl, there have been no new nuclear power plants built in the United States, at least. But the comment that gets made is, if you guys really think global warming is important, you should love nuclear power. Nuclear power can easily solve this problem if it wasn't just for these environmentalists, who are taking socioeconomic problems and turning them into engineering problems. They're not really engineering problems. Well, look, there are really three things. I'll cut to global warming in a second, because global warming actually creates, there's a whole different set of issues. But the normal issues that you guys always hear about, operational safety. There are new designs. I mean, the design that we have, the light water reactor, is basically the same reactor that Hyman Rickover built for the first nuclear submarine, the Nautilus, and it is subject to a famous loss of coolant accident, which we know so well from 3 Mile Island. And the Chernobyl reactor, which had a criticality accident, also there's something inherent in the design of those reactors that the operators can actually screw them up a lot. And I would say if operators can screw it up, it's a design problem. It's not, I mean, you can blame the operators all you want to, but it can have a catastrophic effect. Some of these gas-cooled reactor designs, particularly this pebble bed helium-cooled reactor design that the nuclear community is advocating now, are actually immune to that kind of accident. I mean, even if they lost their coolant, they would still not have a meltdown or spread their reactivity. And I think if that can be proved out experimentally, that has a lot to say for it. But it's obviously not the only problem. The two other problems, which are real biggies, are waste disposal, which, well, I'll get to in a second, waste disposal and weapons proliferation. Now, anxieties about waste disposal and proliferation, whatever you may feel about it, are clearly behind the opposition by the state of Nevada to having a nuclear fuel repository in Yucca Mountain, and also behind the decision by the Pentagon to deploy long-range bombers, a very recent decision, to Guam, capable of destroying the North Korean reactor complex that we worry about so much. I mean, if nuclear proliferation wasn't an issue, which many nuclear people say don't worry about it, there's never been anybody who took a nuclear reactor and made a bomb out of it. I don't think the Pentagon would be putting these B-1s on notice that they should be ready to destroy that reactor. Maybe we can negotiate it away. But, I mean, it's unrealistic to say that these are non-problems. But they might be soluble problems. There are research approaches to treating nuclear waste, to irradiating them with neutrons, and to making proliferation-resistant reactor fuel cycles that might actually work. That's not the problem for global warming. The problem is a surprising one. It's that we can't build these reactors that would work fast enough. See, they all work on U-235. There are no countries that have commercial breeder reactors anymore. There used to be, but not anymore. So all of our nuclear reactors work on the U-235 isotope, which is 0.7% of natural uranium. And if you were to burn all the identified uranium resources in light water reactors, remember you're only burning the U-235 part, it would last between 6 and 30 years, depending on whether you're working with reserves or ultimately recoverable resources. That's clearly not a viable solution to getting this high amount of energy. The only way you're going to use nuclear in a realistic way to do this 10 to 30 terawatt problem. By the way, we now consider 10 to 30 terawatts the amount that we should be shooting for, is if you build breeders. And if you build breeders, you have to start breeding almost immediately. Even the National Energy Plan, Dick Cheney's National Energy Plan, said, well, you can start recycling some of the plutonium in the spent fuel rods, but recycling will only get you about a factor of 2 or 3. The theoretical increase in nuclear fuel that you can get from breeding is a factor of 60 if you breed the U-238, which is most of the uranium, to plutonium, which has its own problems, and unfortunately you can't use the plutonium as a catalyst in a fuel cell. It would be better, most people think it would be better to use thorium and make U-233 from thorium because it's harder to separate the U-233 from the waste stream. It's a more proliferation-resistant cycle. We're doing practically zilch about this in terms of R&D. I mean, we're going in exactly the wrong direction in terms of research and development. If we say, what does that thing blinking 0 mean? Is that for me? That doesn't apply to me, does it? Can I get extra time based on the precedent of the earlier speaker? Okay. You're going to miss such good stuff. Okay. You read the paper. We also looked at fusion. There's going to be a talk about fusion as well. Now, I don't have time to go through the whole story of fusion, but one of the things about fusion is the most successful reactor design it's been to magnetically confine a plasma in this sort of donut shape called a tokamak, a toroidal confinement plasma. We sort of invented this thing by Andrei Sakharov. And although we're still pretty far from a power plant, these guys have worked to the extent that they've produced neutrons. They use a fuel cycle based on deuterium and tritium. Tritium doesn't exist naturally, but the tritium has to be bred itself in a blanket around the tokamak, which has never been built. It would have a lithium blanket. The blanket would be molten lithium. It would get hot, and it would create steam, and the steam would basically turn the same kind of steam turbines that fossil fuel plants or nuclear plants do. Nobody's taken it to that point yet. However, the tokamak has reached the so-called theoretical break-even point. Break-even meaning that the energy that was put in to heat up the plasma to 100 million degrees is approximately equal to the energy that's streaming off the plasma from the neutrons that are produced by the DT reaction. Now, one thing that might be able to come online before fusion reactors is because they can produce such copious neutrons. It's been suggested that you put thorium into the blanket along with lithium and use it as a breeder. In fact, that is what Andrei Sakharov advocated before he passed away a few years ago. One tokamak fusion reactor might be able to produce enough fuel for 15 thorium, essentially beginning thorium breeder reactors, or conventional reactors burning U-233, where the U-233 was made by the tokamak. This way we might at least be able to capitalize on the significant investment we've already made in fusion and maybe do this fission-fusion hybrid. But of course, all of these ideas relating to fusion and fission imply that we're going to be able to solve some of these outstanding problems of fission and fusion. And now plenty of people have already talked about the potential of nanotechnology for energy, the potential for storage of hydrogen, the potential for superconductivity. Those two, I would like to learn more about how real those are. Of course, if you're willing to go into the relatively distant future, can you see this picture at all, or is it just a black blur? Too bad you can't see it. It shows a space elevator, which is a very far out idea, but theoretically possible. If you ever had a structural material that was physically strong enough, we might be able to really cut the cost of going into space by building a space elevator. Not enough time to discuss that. Maybe some of my colleagues from NASA will mention it. There already are some early warning signs, though, about global warming. I just touched on that. The earliest symptoms may have to do with the bleaching of coral reefs. This shows a satellite picture of the reefs around the Bahamas. And of course, we did have this big piece of the Antarctic ice sheet, the Larsen B ice shelf, the size of Rhode Island, break off recently. Again, as has been said, you can't say that any one of these many, many things that are happening that are predicted for global climate change is climate change, but they may be contributing. Let me just give my final summary thing. So what do we want? What do we think is worth doing? An Apollo-like program in alternate energy is needed. And we think that this should cover a very broad spectrum of mitigation technologies. We don't want to go around in a circle and shoot each other over which energy technologies are best. We'll let the market decide that. The U.S. should provide the leadership for this, although it should be an international program. The goal should be to provide options capable of transforming the global energy system to one that can make 10 to 30 terawatts of primary power by 2050. We need to know what are the strategic technologies and demonstrations, and we need to do that could produce user-friendly, energy-efficient, renewably powered communities, zero-emission fossil fuel power plants with CO2 captured, air capture of CO2, hydrogen storage, global scale and smart grids, operationally safe and proliferation-resistant reactors and breeders, wireless power transmission, and space solar power, fusion fission, fission fusion and particle accelerator, fusion power, fission fusion breeders, and particle accelerator hybrids. We also should devote a significant part of this program to leapfrog technologies for alternate industrialization paths, particularly for developing countries. And I tend to favor the solar power satellite demonstration as a collaborative project of the United States, NASA, the IPCC, and developing nations. Maybe we should let the Japanese in too, since it was their idea initially. Nanotech could be a major player. Well, you'll be talking about this after me, if cost barriers form, and this has something to do with molecular assemblers, but maybe not. Okay, that's it. Thank you very much.
Okay, we have a bus coming. We have time for one question.
Yeah. Oh, I'm sorry. Okay.
Very good. I'm Rob Goldston. I'll be talking about fusion tomorrow.
Right.
Just to be clear, Wally Mannheimer, one of your co-authors, is a real enthusiast for fission fusion, putting them together. Sort of the rest of the people working on fusion think that fission is a nearer-term option. It will take us a while to bring fusion online, and making fission depend on fusion or vice versa may not be the best way to get, for example, the non-proliferation advantages of fusion.
Well, you understand, our reason for this is uniquely something that fell out of the analysis. It's the need to breed very rapidly. We don't think conventional breeder reactors can make the 10 terawatts in 50 years fast enough. Go ahead.
You have used, I believe, the DOE statement about resources of uranium.
No, we
formally,
use International International Atomic Energy Commission.
Those
sources.
who are advocating breeder reactors soon like to use a number which does not agree with the number used by most people for conventional resources of uranium, which would suggest we have about 100,000 gigawatt years of uranium.
Well, I don't know that it's even productive to argue because I'm not an expert, but what I do feel is that these numbers come from standard sources. If there's a lot more uranium than the numbers that we used, that would change the conditions. And, for example, if there's twice as much uranium in resources, in reserves, there's practically nothing. I mean, that only gives us 6 years at 10 terawatts. Now, the numbers are calculated in a footnote to the science paper, and if we made an arithmetic error, please write a letter to Science and correct us.
Well,
I don't think we did.
the issue is that talking about 10 terawatts with fission on anything like a timescale of 50 years is totally unrealistic. So if one talks about realistic numbers, as I will tomorrow, a terawatt by mid-century is a stretch. And then uranium resources aren't an issue, and then there's no need to be going off on breeders.
Thank you very much for making my point. That was exactly our point. That if we're interested in mitigating global warming, we're going to need 10 to 30 terawatts from something. Now, I didn't even talk about biomass. If you wanted to get 10 terawatts from biomass, you need 20% of the Earth's surface, and that's all the land we use for human agriculture. Now, I think that we should try to solve this problem, but if we're going to solve the problem, I think we have to use real numbers. And it's a different problem if you just want to restart fission, because fission is stagnant. You have a different problem. If you just want to get renewable, then to use fission to mitigate global warming, because the amounts of energy that you need and the times that you need it are very different if you just want to get fission going again. This is the same thing is true of renewables. If you just want to make photovoltaics viable, you don't have to produce 10 terawatts by photovoltaics. But if you want to produce 10 terawatts by photovoltaics, you have an enormous issue of scale-up, and you have that issue of scale-up whether you're doing CO2 sequestration Or now you're shaking your head. Maybe you're shaking your head because you think this job is impossible or isn't worth doing. But that's not the question we asked. The question we asked is, if you were serious about mitigating global warming and put in a reasonable amount of economic growth and a reasonable amount of improvement of energy efficiency, how much energy do you need and where can you get it from? And that leads you to ask very different questions than people have been asking. And there are surprising answers, and I didn't even get into anywhere close to some of the other things that we found, which were also very interesting.
Listen, thank you very much. A little house cleaning. We will all meet back. The conference will begin again at 8 tomorrow morning. For those of you who are in my science speaker guest list, the bus is going to be out front at 5:30. So if you join us all in the front foyer, we can pack up and go to dinner.
Okay, great.